Well, so let us solve one more problem from CSIR Net 2020, question number 75, and this is basically from nuclear physics cell model. In this question, it is mentioned that the magnetic moment of a proton, that is 2.792 in the unit of mu n, and also they have mentioned the magnetic moment of a neutron is given as minus 1.913 in the unit of mu n. Now we have to calculate the magnetic moment of fluorine nucleus with atomic number 9, mass number 90. In fact, we have to calculate the magnetic moment of neon nucleus, atomic number 10, mass number 19 by using cell model. Okay, so to calculate that magnetic moment, we have to first calculate that nuclear spin. And as you know, that nuclear spin of any nucleus will be arising because of unpaired nucleons. So if we take that example of fluorine 919, we can see here the number of proton, that is 9, and number of neutron is 10. So this all 10 neutrons are basically paired. So they will not contribute to the nuclear spin of this nucleus. But here you can see that number of proton is odd, so we'll have unpaired protons. So if we fill them, we'll have first on a sub that will contain 2 protons. In the next cell, you'll have on p3 by 2 that will contain 4 protons. Next cell, you'll have on p half that will contribute 2 protons. In the next cell, you'll have on d5 by 2 that will contribute on proton. So you can see from here that last unpaired proton is staying at d5 by 2. So obviously the nuclear spin of this molecule or of this nucleus will be 5 by 2, and that is basically locating at L plus half, because for d orbital L is 2 and J we can see from here that is 5 by 2. It means that is this unpaired proton is staying at L plus half state, and we know when that last proton is staying at L plus half state, the magnetic moment of this nucleus will be arising because of proton, and that will be J plus 2.29 in the unit of mu n. Now if you substitute that value, J is nothing but 5 by 2, that means 2.5 plus 2.29 mu n. So that will be 4.79 mu n. That will be 4.79 mu n. But according to given option, they ask for closest number. So if you see that closest number, whatever we have obtained, that closest number according to the given option, that was 2.62. So this number was closest to 2.62. So that we can take that the magnetic moment of this nucleus will be 2.62, because this was only the closest to 4.7, and all others number was very large. So we'll take this magnetic moment of this nucleus. Then you have a neon. Again, if you see here, protons are paired, but neutrons are actually unpaired. So we have to fill them. That neutron we have to fill. In the first cell, you will have again on S half that will contain 2 neutrons. In the next cell, you will have on p3 by 2 that will contain 4 neutrons. In the next cell, you will have on p half that will contain 2 neutrons, and the last neutron will be staying again at on d5 by 2. So obviously the nuclear spin of this nucleus, again it will be J equals to 5 by 2. But this is contributed by neutron and having J equals to L plus half condition. As you know, for a magnetic moment when contributed by neutron because of its unpaired nature, and when J equals to L plus half, the formula is the magnetic moment of this nucleus is mu n. Mu n means that is arising because of neutron, that will be minus 1.913 mu n. Okay, so according to given option, that was close to minus 1.88 mu n. Okay, so according to given option, magnetic moment of proton, magnetic moment of fluorine nucleus will be 2.62 mu n, and magnetic moment of this nucleus will be closest to minus 1.88 mu n. Okay, So this is the correct option. Thank you.